All right, lesson 6 in unit 7 of Calc BC at Canandaigua Academy deals with what we call improper integrals. What is it that makes an integral improper? Well, there are two kinds of improper integrals. We'll deal with the one and then with the other. First, integrals with infinite limits of integration are improper integrals. Integrals with infinite limits of integration are improper integrals. If your integral goes from a number to infinity, from negative infinity to a number, from negative infinity to infinity, all of those are improper integrals. And how we handle them is actually pure genius. We say, I don't know how to deal with the infinite, but I know how to deal with the finite. So we'll deal with the finite. If f is continuous on the half-open interval from a to infinity, suppose it's half closed, then the integral from a to infinity of f of x dx is. So the thought is, I don't know how to do the integral from a to infinity, but I do know how to do the integral from a to some number b. We'll say that b is larger than a. And I know how to make b very large. And so we combine those two skills, and sure enough, we say the integral from a to infinity is the same as taking the integral from a to b and letting b get infinitely large. If f is continuous on negative infinity to b, then the integral from negative infinity to b of f of x dx is, well, we take the integral from a to b and let a get larger and larger in a negative direction. Well, what if f is continuous from negative infinity to positive infinity? Then the integral from negative infinity to infinity of f of x dx is the integral from negative infinity to c. Just pick any c, but then use that c again. In the case where the integral runs from negative infinity to positive infinity, we say, wow, I don't know how to do that, but I do know how to do this, and I do know how to do that because of rules 2 and 1. So we just use this rule for the first one and that rule for the second one. So what the heck? Let's evaluate the integral from 2 to infinity of 1 over x dx. Looking for the area under the graph of 1 over x from x equals 2 all the way out to the right. I know how this works. This is a type 1 improper integral. It's not really called a type 1 improper integral, but if you were on the other slide, it'd be definition part 1. So the integral from 2 to infinity of 1 over x dx is the same as the limit as b approaches infinity of the integral from 2 to b of 1 over x dx. I don't know how to deal with the infinite, so I set up a finite integral and let b get infinitely large. Well, I know how to do that because my calculus teacher has been pretty good. I'm going to take the antiderivative of 1 over x and evaluate between 2 and b. And I know how to do that. I've got ln b minus ln 2. And the question is, what happens to that thing as b gets large? Well, ln b gets larger and larger and larger. ln2 is a constant. This goes to infinity, which means that this integral diverges. It has infinite, it represents infinite area. Well, wouldn't they all be infinite? He asked as if example 2 was a counterexample to that. It's a small change. It's a small change. Not a very big change at all, just a little superscripted 2. And yet things are very, very different. The integral from 2 to infinity of 1 over x squared dx is the limit as b approaches infinity of the integral from 2 to b of 1 over x squared dx. And I know how to handle that because my calculus teacher wasn't too bad. The antiderivative of x to the negative 2 is x to the negative 1 divided by negative 1. That's negative x to the negative 1. That's negative 1 over x. Oh, sorry. Sorry. That's a b. Was it a b up top? It was. Okay, good. Now you don't have to yell at me tomorrow about that. Limit b approaches infinity of negative 1 over b minus negative 1 over 2. So we ask ourselves, what happens in this case? Well, as b gets larger and larger, 1 over b gets closer and closer to 0. 1/2 is 1/2. We get 1/2. This integral converges to 1/2. Yeah, this is a bizarre reality for us, by the way. This is a bizarre reality. Sometimes you take an integral from, oh, magic pen. Sometimes you take an integral from a finite number to infinity and it diverges. Sometimes you take an integral from a finite number to infinity and it converges. Ah! I want to give you a couple of things to think about with that. Couple of things to think about. Things that you should think about, probably try to do before we show up in class together. One is that integral. That integral. And I give you that one because, oh boy, what the heck? This is a factorable denominator. Do you remember how we did integrals with factorable denominators? And the reason I give that to you is because the College Board is going to give stuff like that to you where they try to test that kind of integration in the context of an improper integral. The other thing to think about is this integral. That is an integral on an infinite interval of a product of seemingly unrelated quantities. And so that makes me think about how we do integrals of that kind. College Board is really good at putting unconnected things or semi-connected things together in the same problem. But wait, there's still more. Integrals of functions that become infinite at a point within the interval of integration. are improper. So if your interval is infinite, you're improper. And if the function goes to infinity somewhere, you're improper. How do we handle that? If f is continuous on the half-open, half-closed interval AB, then the integral from a to b of f of x dx is. We should talk about this. This is some case where the function goes to infinity at a. So how do we handle that? We take a finite integral that we know how to do and let c get closer and closer to a from the right. Similarly, if f is continuous on the half-open, half-closed interval AB, then the integral from a to b of f of x dx is the symmetrical case. We take a finite integral that we know how to do, and we push that limit toward the part that gives us trouble. If f is continuous on, let's just be ridiculous, then the integral from a to b of f of x dx is the integral from a to c plus the integral from c to b. All of our properties of integrals from Unit 4 still apply. Basically, if you've got a vertical asymptote, you take a finite integral that gets close to that asymptote and then use the limiting process to push the integral toward that asymptote, like this. Integral 0 to 3, 1 over x minus 2 to the 2/3 dx. Of course, the issue here is that this has a vertical asymptote at x equals 2. And so we're going to add two integrals. We're going to add the integral from 0 to 2 of x minus 2 to the negative 2/3 to the integral from 2 to 3 of x minus 2 to the negative 2/3. We're going to see what happens with that. So I ask myself, in the red case, we're going to take a limit as b approaches 2 of the integral from 0 to b of x minus 2 to the negative 2/3 dx, which happens to be the limit as b approaches 2 of, now I need an antiderivative of x minus 2 to the negative 2/3. So I'd raise the power by 1, that's 1/3, divide by that power, so I've got 3x minus 2 to the 1/3 evaluated between 0 and b. So what is that? Substitute b, so that's the limit as b approaches 2 of 3 times the cube root of b minus 2 minus what I get when I substitute 0, and that's 3 times the cube root of negative 2. Well, what's that? That's b approaches 2, that cube root drops, negative 3 cube root of negative 2, which is just 3 cube roots of 2. Plus, we do the same thing over here. Going to take a limit as b approaches 2 of the, we probably should use a. a approaches 2 of the integral from a to 3 of x minus 2 to the negative 2/3 dx, which says limit a approaches 2 of 3 times x minus 2 to the 1/3 evaluated between a and 3, which is the limit as a approaches 2 of, let's see, 3 times 3 minus 2 is 3 minus 2 is 1. 1 to the 1/3, that's 1. Minus, sub in, 3 times the cube root of a minus 2, which happens to be 3 minus 0. Got it? I take an integral of a function that shoots up to forever, and it doesn't matter. In this case, I get a finite answer. Could have got an infinite answer with a different kind of function. Could have. Could have. I will leave that with you. I'll give you one to think about. We'll talk about it next time. We'll talk about this next time. Integral from 1 to 3, 1 over x minus 3 squared dx. If we were to write that out as a limit of a finite integral, find an antiderivative, sub, and subtract, use the limiting process, what would happen to that? Well, you might think, well, by the fundamental law of textbook examples, this has to be an integral that diverges, and I say, well, unless I thought you would think that way. So I'd work it out if I were you. Awesome. Hey, we'll see you tomorrow. Be glad to do it. We'll practice. It'll be good.